All right, so we're going to take a whack at some of these integrals here. The first one that I want to evaluate is the integral of x over x to the fourth plus 9. Now, at first glance, I'm looking at this and I'm seeing a rational integrand, a rational expression. And my first instinct is to say, maybe we should try integration by parts. However, that would require me to factor this denominator. And as written, I would say that this is not factorable. It's an irreducible quartic. So that means a fourth degree polynomial. It's an irreducible polynomial. It's not clear to me how I would proceed with integration using partial fractions. So then the next question is, okay, we've seen examples of rational expressions where it's actually easier to use a u substitution. But what would I set u to? If I set u equal to x to the fourth or x to the fourth plus 9, for example, then my du would include an x cubed term, and I don't have any x cubeds anywhere. I have an x, but I don't have an x cubed. So what do I do with that? Well, this is going to be a case where we have we're still going to make a u substitution, but it's a slightly less obvious one. So here's what's going to be helpful. I'm going to write my integrand in just a slightly different form. What I'm going to do is I'm going to change this x to the fourth term to an x squared, like that. Okay? X squared. And my reason for doing that is now I see an x squared term, which to me feels like a good choice for u. And the reason for that is because the du is going to be 2x dx, and that x there is making an appearance in my integrand. Divide both sides by 2 to get an exact match. So I have x dx, x dx. Let's make the substitution now. So I have this 1/2 that I know is going to get pulled out of my integral. This x dx is going to become the du. The 1/2 has already been accounted for out there. Now, that x squared in parentheses becomes u, but then I'm also squaring that. So I end up with u squared plus 9, okay? Now that is an integral that's in a form that I recognize. This thing, if I go back to my table of integrals on the first page of my notes here, so let me find that right here, is exactly of this type, right? X squared, or in our case, u squared, plus something else squared. I have a 9 in my example, which means that a that's being squared would be a 3. And we know that this integrates out to an arctangent function. So right away, I know what this looks like. 1/2 times 1 over a, which remember we said 1 over a would be 1/3 actually in this case, times the inverse tangent of x over a. So u. I have to remember that we're working with u right now. U over 3 plus c. And now I want to convert my u back into an x squared to finish this problem. 1/2 times 1/3 is 1/6. Arctangent of x squared over 3 plus c. That would be my final answer. Okay, so our strategy worked. We found a non-obvious u substitution that ended up working here. All right, let's take a look at this one. This might initially be an intimidating integral because it looks complicated. It involves the natural log function in a couple of places. So you might look at this and think, geez, I don't really know even where to start with this one. I do see a radical here. Maybe this is a place where I would use a trig substitution or a hyperbolic substitution, because we know that those show up where radicals appear. But it's not immediately obvious how that would work. So instead what I'm going to do is I'm going to take a look at my integrand and see that there's a couple of these natural logs showing up in there. It might be beneficial to use a u substitution where we set u equal to the natural log of x, really just because it keeps showing up. So I'm going to set u equal to the natural log, which means du is equal to 1 over x dx. Okay? Now here's what's cool about that. This x right here is in a denominator, so I could think of that as 1 over x times the rest of this stuff. I actually have a 1 over x dx appearing in my integrand. That tells me that I can do some work simplifying this. Okay, so that natural log of x becomes u. The square root of 1 plus natural log of x squared becomes the square root of 1 plus u squared. And then the 1 over x here and the dx there together make up my du. All right, now looking at what I have here, this integral looks simpler than what we started with. And it looks like there is a substitution that would be helpful here. 1 plus u squared. If I set that equal to another variable, let's make it a w, because we can't use u again. I've already used u. Then that would mean dw is equal to 2u du. If I multiply both sides by 1/2, I get u du, which is appearing in my integrand. So a second substitution helped out with this problem. Okay, so I know that the u du is going to become the 1/2 dw there. Let's pull the 1/2 out. And if I look at what's left, I have the square root of 1 plus u squared, which is going to become the square root of w now, but it's going to be in the denominator. So a better way of writing that is w to the negative 1/2 power. There's my dw, okay? That's an easy one to integrate. It's going to become 2 times w to the 1/2 power plus c. And now we're going to do some simplifying and including of or resubstituting our expressions back in, so we get back to x's again. 1/2 times 2 is just 1, so that goes away. W to the 1/2 power is the same thing as 1 plus u squared to the 1/2 power, or 1 plus u squared under a radical. And then that u was originally defined to be the natural log of x. So I end up with 1 plus the natural log of x squared plus c. And that would be my final answer there. Okay? So what was unique about this problem is it required 2 u substitutions. But we eventually got there. Okay? Let's take a look at another one. This one's got some trig. I want to evaluate the integral of 1 plus tangent of x quantity squared times secant of x dx. Okay, you might be tempted to look at this and think, okay, I might be able to try some kind of a u substitution right off the bat, because I know that tangent, when I take its derivative, I get a secant squared, and I see a secant in there, but I don't see a secant squared, so maybe that doesn't work. You kind of talk your way through it a little bit. And for this one, I think a good place to start is to simplify the integrand, or manipulate it in a way that puts it in a better form. So I'm actually going to square the stuff in parentheses, because that's what it's telling me to do. Now, if I squared 1 plus tangent squared, I'm going to get 1 plus 2 tangent of x plus tangent squared of x. Then I have the secant of x dx sitting on the outside, right? Within this the set of parentheses here, I see a trig identity that I can use. 1 plus tangent squared is equal to secant squared. So that means I'm going to get a secant squared of x plus 2 tangent of x times secant of x dx. At this stage, it makes sense to me, since we already squared this thing, to distribute that secant of x in. And here's where I'm going to get secant cubed of x plus 2 secant of x tangent of x dx. Now, you may remember in our strategy in the previous video, I had mentioned the secant cubed function. And we said that, you know, it takes a little bit of work to integrate the secant cubed function, but we've already done that in a previous video. So I'm going to reuse my solution to a problem I've already done, so I don't need to go through all that work again. Back then, we found that the secant cubed function, when we integrate it, gives us this: 1/2 secant of x tangent of x plus 1/2 natural log of the absolute value of secant of x plus tangent of x plus c, of course, but I'm going to save that for the end. Yeah, it's nice not having to go through all of the work to get to this stage. We're just reusing previous work. And then this second term right here is ready to be integrated, because the integral of secant tangent is just secant. So that 2 there isn't going anywhere. I get plus 2 secant of x. And then I'll put my plus c at the end. So that worked out really well. Okay? One last example. I want to evaluate the integral of dx, or I could think of that dx as being out here and just call it 1 over the square root of 1 plus x plus the square root of x. So this is one of those examples where manipulating the integrand is really, really helpful. And we're going to use the same technique that we talked about in step 4 of our strategy in the previous videos, namely multiplying by a conjugate. You notice my denominator has something plus something. I'm going to multiply that by a rational expression whose numerator and denominator look almost the same as that, but I'm going to swap the plus out for a minus, like this. Okay? Now, if I were to do that, my numerator is now square root of 1 plus x minus the square root of x all over. Now, when I multiply these things together, what I'm looking at is like the factored form of a difference of squares. So the multiplication is going to give me this thing squared minus that thing squared. Or in other words, 1 plus x, squaring it removes the radical, minus x dx. Now this is really, really cool because what ended up happening is I have x minus x, which is 0, plus 1, which is 1. This whole thing is just over 1. And now I can rewrite it, and I'm going to write it this way. 1 plus x to the 1/2 power minus x to the 1/2 power dx. Okay? I wrote it to the 1/2 power because it's a little easier for me to see how to integrate that. Add 1 to the exponent, which gives me 3/2, and then multiply by the reciprocal of that, 2/3. I'm going to be doing the same thing here. So let's take the 2/3 that's already going to appear in both of those antiderivatives, and I'm just going to pull it out completely. That's going to leave me with 1 plus x to the 3/2 power minus x to the 3/2 power plus c, all times 2/3. Okay, so hopefully with those examples, we've kind of illustrated how to use our strategy in different contexts. And there were examples that we could have done but didn't that use other parts of that strategy. For example, we didn't do anything that required integration by parts. We didn't do anything that required a trig substitution. You'll see examples like that in the homework, but use this strategy that we've outlined to determine when to use which of those strategies. But that's going to wrap up 7.5 for us.